Добрый вечер.
Добрый вечер.
Не знаю.
Можно спросить, эта статья на архиве есть у вас?
Ну, я еще не выложил, она готова, в общем. Я хочу ее выложить только после того, как вот, учитывая все, ну, как сказать, ошибки, которые
Ну,
в ходе доклада
вряд ли
выясняются.
мы найдем ошибки прямо уж так.
Нет, ну, я имею в виду скорее ошибки в изложении,
Мгм.
а не другие.
Методологические, что ли?
Ну да, да. Нет, но рассказывая людям, я понимаю, что что-то я неправильно вообще, не в той последовательности или вообще неправильно рассказываю. Особенно после того, как все совершенно запутались, становится ясным, что все надо переписывать. Я вот обнаружил, что на планшетке Zoom не дает возможность аннотировать, а на Маке дает. И на десктопе тоже дает. То есть на Ubuntu.
Странно. Я вроде бы в прошлый раз случайно что-то какие-то эти самые каляки-маляки заводил.
Это когда открывается доска вроде вот. Когда
Ну,
Blackboard открывается, то да.
Ну, посмотри на экран.
Вот,
Это
очень
не
хорошо.
Blackboard.
А вот у меня не получается. Почему же...
Я только не знаю, как теперь это убрать. Сейчас попробую.
Вот, слушай, ну, может быть, мне переустановить его, что ли?
Может быть, ты просто не видишь, как это сделать. Значит, я это делаю так. У меня, когда показан экран, там в левом углу, но он иногда скрывается. Нужно вот на левое черное поле тапнуть, после этого появляется кружок, в котором ручка. Вот если тапнуть на ручку, появляется меню для рисования.
Слушай, вижу. Значит, точно. Вот у меня получилось.
Проблема просто в том, что вот этот интерфейс, который связан с нежными поглаживаниями экрана, он идиотский и людям нашего поколения недоступен.
Все, да. Я когда-то даже это знал, но забыл. А теперь вот ты мне напомнил, да.
Да я на прошлый раз просто случайно это заметил. До этого я как-то не задумывался, как это делать.
Угу. Ну, давайте, может быть, я начну, поскольку это...
Ну, наверное, да, уже можно начинать.
Switch to English, Саша?
No, since Toma is here, I guess we should switch to English.
Yes, I'm
Okay.
here.
Yeah,
Okay.
yeah.
Okay. Should I probably recall the contents of the previous talk? So, very briefly, to this end, I need somehow to change pages. So we consider substitution. Substitution is a mapping that assigns to each initial proto-tile a so-called macro tile, which is a tiling of the tiles from the set of some stretching of the initial tile, like here or here or here. Substitution will be denoted by letter sigma, and sigma t denotes the tiling which is obtained from a tiling t when we substitute each tile by the corresponding macro tile. And the result of applying substitution is called decomposition of a tiling. It is denoted by sigma t. And composition is the reverse operation. We say that t prime is a composition of t if the other way around, applying the substitution to t prime, we obtain t. In general, there might be many such t prime or no such t prime at all. A tiling is called substitution tiling if every its part is a subset of a super tile, and the tiling is called hierarchical with respect to distribution if there is an infinite chain of its composition. That means an infinite sequence for which the first tiling of the sequence is the original tiling, and the decomposition of each tiling is equal to the previous one, or the other way around. Each tiling is the composition of the previous one. Further, we will assume that all super tiles are side-to-side tilings. That means that all tiles, adjacent tiles, either share a side, the entire side, or do not share any segment of positive length on their side. I have proven the theorem that every substitution tiling is hierarchical. but the reverse is not true in general. And let's skip this about crons because probably we won't need it today. So there is some theorem in reverse direction when hierarchical tiling is substitutional, but we do not need it today. Substitution is one of the means of defining tilings, and the other one is the so-called local rules. When we have a tile set and define finite number of finite patterns that are forbidden to meet in tiles. And if a family of tiling can be defined using local rules, we call it SFT, which is abbreviation for subshift of finite type. And the main definition for my talk is the family, Sophic family of tilings. We call it family tau T. Sophic if there is a decoration of tiles and some SFT T prime with the property that any tiling belongs to the original family if and only if it's is obtained from a tiling from that SFT by erasing all colors. And here are previous work. So Moses theorem states that under certain assumption on substitution, the family of substitution tiling is Sophic. Goodman-Strauss proves that under my much weaker, but unfortunately unclear assumption, the same holds for a larger class of substitutions. And Fernicat-Langer proved similar theorem for hierarchical tilings. But the problem with their paper is that the proof is only sketched, and actually the technique works under much weaker assumption than claim.
Weaker or stronger?
Under stronger, sorry. The same errors I didn't correct it. Under stronger.
Yeah, okay.
So my contribution is that I will state, I have stated some clear assumption on substitution for which both families are Sophic. And I think that if the audience will have enough patience, I will state this assumption tonight. So I ask you for some patience because
before midnight, you mean, yeah?
Because they will look strange without understanding how the technique works. It is hard to understand why we need that or that. But still, I don't see any other way to state the theorem in a clear way. So my assumption is that there is a markup of all macro tiles of the original substitution that meets certain conditions. So what is the markup? So I made now for this talk much more pictures to make it more understandable. So first I need to introduce some terminology. So the tiles from initial set are called prototiles. And what you see in macro tiles are shifts of the initial prototiles. We call these tiles types. So for this particular substitution, there are 2 prototiles and 18 different types. And we will assume that different types do not overlap, so they are written on a plane.
But when you say types, it's types of something or just types?
No, we will later say that some tile of our set have a certain type.
Ah,
Uh,
but now it's just
types.
parts. Yeah.
Just types. And so what is a markup? To mark markup as a substitution, we have to do 4 things. First, to assign to each side of each prototile a name. For example, for this substitution, we need to assign 8 names. Some of them may coincide. And here is an example. So the simplest substitution is when we substitute 1 square by 8 squares. And here are type names
9.
A, B, C, D. We will assume that for a given prototile, all these names are different. Second, we need to choose a central, the so-called central type in each macrotile. That means oh, sorry, you do not see.
Probably it's written type there, I guess.
Let's see. I can make it smaller. A little bit smaller, I guess. How to do it smaller?
So this is a type center.
This is a center, yes.
Yeah.
But still.
And what is written here is not clear, but maybe you can just say, and we will remember this.
But this bothers me. Why I can't move it?
Because you are in a presentation mode.
I see. Like that.
Oops.
That's my problem. So when I compiled it, I made the picture. Okay. So yes, the left arrow points to the central tile type, right? Third, we need to
and
choose
the green cycle is called somehow, which we forget.
Connecting graph. The green ring is called a connecting graph. We need to choose a connecting graph, not necessarily a ring, but usually it's a ring. And also to choose a net. This is blue graph. The net graph will be, when I say graph, I mean that this will be a subgraph of the dual graph. The dual graph consists of all types. 2 types are connected by an edge if they share a side. And outer edge are called hanging edge of the connected graph. And blue and green graphs should be a subgraph of this graph. And also, I will use the terminology main ports. Main ports are those outer sides of tiles that belong to the net, to the blue graph. And
so we have 4 of them.
There are 4 of them here.
Yeah.
On all the remaining outer sides are called secondary ports. Is this clear? What is a markup?
Seems so.
Okay. Now,
there's a lot of condition which you didn't say yet.
Yes, of course, there are lots of requirements, and I proceed to the requirements. So these are other examples of, this is the first example of markup. This is the second, and the central tile is always in the middle of the macro tile. Second example, and all these 2 examples, and also this first example will satisfy all the requirements. So why I've chosen them to demonstrate.
The names are not chosen, not shown.
The name is not shown, but in these examples, the name are, so to say, unique. each name is used only once for one side of one prototile. So the names are, so to say, obvious in these three examples.
But, you didn't say who gets the names. So you get the names for the sides of the
names,
prototiles and also something else.
No. The names are provided to all sides of all prototiles.
But not types.
Not types,
Yeah.
prototypes. I think I have written here. No, I forgot to write it. So names of sites of prototypes. It's written, Sasha, number 1. To assign to each side of each prototile. And
Okay, but since there are no requirements, now it's not clear what we
not
should
clear,
achieve,
of course. And here is the requirements. And also I need one more notion: extendable and not extendable prototiles. It might happen that the central tile has the same number of sides as the initial prototile. Such prototypes are called non-extendable. And it might be that it has more sides. And this then this initial prototile is called extendable. And one requirement will prohibit that it has less sides than the initial prototiles. So we have either extendable or non-extendable. Yeah, right.
No, I didn't get it, to be honest. So once again, the
No,
prototile.
you don't say what is the center, so it's not clear.
But take any tile which is inside, strictly inside, really any inner tile. So in the first example, it
should be square.
And in the second, it's also square.
And if I remember correctly, if it's a square, that only three sides of this type are used for the connecting for the
net.
Net, yeah.
Right. Right.
So I don't know. Once again, so this first is extendable because it's just a triangle. So it has 3 sides, and inside it has triangles.
And the centers will have 4 sides. And so we do not use all 4 sides, we use only 3.
So
the central tile,
because 4 is bigger than 3.
Right.
Yeah. No, it's not clear.
The second one is not extendable because 4 is equal to 4.
Yeah,
right.
It's a bit strange because extendable assumes that there is some way of extended, but here it's not clear what is the way.
And what would be a better term for this?
No, I don't know what you want to say.
Okay. This is the requirement. So there are 3, so to say, obvious requirements. I will just read it aloud. The net should connect each macrosite. The net is a blue graph. Each macrosite to a side of the central type. Different paths in the net cannot share edges, but they can share vertices. There is at least 1 secondary port on each macrosite. Actually,
if we take 2 paths to different sides, connecting them to the center, they can intersect, or they should keep the ordering.
They can intersect, but can't share edges.
Yeah, but it's possible that the ordering of the name of the ordering, if you go around the clock,
right.
It can be different.
It's possible. It's allowed. And this there is at least 1 secondary port on each macrosite. Actually, this is a requirement for the initial substitution. It just stipulates that each macrosite has at least 2 sides. So one of them is the main port, another one is the secondary port. So the second requirement is about connecting graph. It should be connected. It can't share edges with the net graph. It should include all types on the boundary. And and the last requirement, what Sasha already mentioned, if the initial prototile is extendable, that means the central type has more sides than the initial prototile, then the connected graph must also contain the central type.
Sorry, for the previous one I missed. So secondary port is what? Main port is just a part of the net, which goes to the secondary port.
All the remaining outer sides are secondary.
Yeah. Just and they will go, this circle, this line connecting graph will go through them by requirement.
Like this.
Yeah.
Or like that.
Yeah.
And the last requirement is very easy to memorize. I assume that two macro tiles are shifted so that they share a macro side, and so they are shifted so that they do not overlap. And also, it happens that the resulting tiling is side to side. So each macro side is adjacent to macro side and also side to side. And then every main port must be adjacent to a main port. And as a consequence, also secondary port, every secondary port is adjacent to a secondary port.
Okay.
So these are sort of easy requirements. And the other ones are...
These are all in the Ferny-Collinger paper, you agree?
Yes.
For the moment.
Yes. Actually, it's formulated a little bit in a different way, but it's not important, I guess. And here are new requirements. So the first one is a requirement about the name of sites. Actually, there are two requirements. First of all, if we can shift to prototiles so that they do not overlap and share a site, then the common site, the shared site, must have different names. So here are good example, this one. So however you shift them, the shared site will have different names. And this is bad example. Sasha, do you see why it's a bad example?
Because there's A.
Because they can share this A site, which has the same name. Actually, when we two sides of different tiles have the same name, we will call them eponymous. And the second one is the following one. Consider the net paths. They should connect, each net path by definition connects a macro side to a side of central tile. And this should be sites with the same name, eponymous. And the name of a macro site is just defined as the name of corresponding site. Sasha, do you see why this example is good?
No, what I see that this is just you introduce the names of the so you take the names the names A, B, C, D on the macro tile are just copied from the prototile, yeah?
Right.
And
exactly.
the names of on the center are copied from the other prototile.
Right.
So for example, if it is important that it is red, not yellow, because otherwise we cannot have different names.
So red and yellow have different different names. Actually, the names are the same, but on different sides. A, B, C, D, both. But the names are rotated, as you can see.
Yeah.
And that's why these paths should also rotate 90 degrees counterclockwise. And here, So this is a bad example, and this is a good example.
But you didn't show. Here is the
This
bad
is
example.
a bad example. It's bad because the path connects A and B. This is the macrosite named B, and this is the site named A. So it's forbidden to connect them. Also, it connects. Also, it makes 4 such mistakes. This marker.
But you can make also this things going like this and correct this. Yeah.
No.
If why? If this B goes to that B, and
we
this
can
C
correct
goes
it.
to this.
Wait.
No, of course it depends on how are the. Just you can go from here and from here and then all the requirement will be fulfilled.
But in the left column, the pictures are identical. Why one of?
No. But bad means that everything is bad. Something is bad. So the first column is still okay. But here we have some violation which can be corrected by changing the path. Just to understand what is the requirement.
Right. We can correct it. Right.
Yeah.
And actually, in the last talk, I tried to explain this without the word name. The point is that there is an optimal way to assign names. How it's done? If a path connects certain site of a macro tile to a site of central type, we just say that
this creates some requirement of coincidence between some sides of some macro tiles.
Right. And we consider the equivalence relation on sides of all prototiles. That is the smallest equivalence relation connected, including those pairs.
Transitive closure. But if this makes 2 sides of one prototile equivalent, that's bad. That's what you are saying.
Right. If this naming violates the first requirement, that's bad. Otherwise, the requirement is fulfilled. So actually, we do not need to think how assign names. I just take this particular naming and verify if it satisfies the first requirement.
Okay.
Good.
Now, there is a requirement, a very strange, which is called 2/3. In any non-central type, less than 2/3 of its sides belong to the net. And here is a requirement. Here is an example where it is met. In these examples, our tiles are non-convex octagons. And in the case of octagons, 2/3 actually means that 4 of the sides may be net sides. 4 of 8 is 1/2, and 1/2 is less than 2/3, of course. And you see that in this picture, every tile has at most 2 sides.
At most 4.
At most 4.
Yeah.
Some of them do not have at all. Some of them have 2.
Sorry, but 5 from 8 is less than 2 from first.
No.
5 is impossible because if you go in, you should go out.
Right. 5 is actually impossible.
Sorry.
And where you see 4 here?
4?
Here.
Or here, for example. Right. And actually in several places. In 2 places.
Sorry. Yeah, it's a blue sheet.
Blue.
Yeah. No, I should say that each new requirement is more ridiculous than the previous one.
Right,
but
exactly. But still have patience.
Okay, a bit of.
A lot of
A lot of. Okay.
patience.
Okay.
And here is an example when it is not met. Why it is not met? Look carefully.
Well, there is a triangle, I guess,
Right.
where
Right.
in the center.
And
Well,
2/3
maybe it's a
of
simple-
3 is 2.
No, but the center triangle is okay. What is not okay
Yeah,
is
central-
this.
Yeah, central
yeah,
tile
but-
is okay. Right. This
Yeah,
is
So
but
here is the
two sides of
center.
triangle is also bad, yeah.
Yeah, this is the center, of course, right.
Yeah, but 2 out of 3 is just 2/3.
Right.
Yeah.
And we require strictly less than 2/3.
Nicolas,
Right.
will there be some duck lemma at some point with this name?
Duck lemma,
Yeah.
not tonight, maybe the next time.
Ah, okay. But okay. As far as I understand, it's rather connected to the duck lemma.
Right. It is needed for the duck lemma, which is now called some hotels. But
I like duck lemma.
Okay.
And here is even more ridiculous requirement called cyclicity requirement. So consider the following function. It maps each central type to the central type which is in. So consider only central types and apply to each of them a substitution and take the central type in the resulting macro tile. This is the value of our function denoted by C. For example, here the function C maps blue central type to green and green to blue. And here in the second example, it maps green central tile to green central tile and the second green central tile also to green central tile.
No, C maps in which direction? For example, in this picture, it maps blue to green or green to blue.
Here it maps this green to blue.
Okay.
So
Okay.
it acts only on central types.
Yeah.
Each central type is just considered as prototile. We consider the result, its image under substitution, and take the central type in the macro tile. And this is the value of our function. So here we have 2 central types, and here we have also 2 central types. But in the first example, they are of different colors. In the second, they are of the same color. Okay.
But I don't understand. If we apply, no, I don't understand. We apply to central tile. So this central tile is mapped to this one.
Right.
Here. And this one is mapped also to this one.
Let me write here. So here, call it 1 and 2. So 1 is mapped to 1.
Yeah.
And 2 is mapped also to 1. So we obtain the following function. This is the function C in this example. Here, call it 1 and 2. 1 is mapped to 2, and 2 is mapped to 1 back. So here is this function, and here is this function.
Yeah. So in this example, it's not cyclic, but weakly cyclic, because we don't have non-extendable central types, or we have. Non-extendable is what?
Here everything is non-extendable. So.
So this is not cyclic. This
so in the first example, both types are cyclic.
Yeah.
They belong to the cycle.
Yeah.
In the second, 1 is cyclic, but 2 is not.
Yeah, but non-extendable is when there's too many edges or
the same number of edges.
So for this example, the requirement in the weak form is false.
For the first, in the weak
For the
form is
second.
true.
No, for it's even for the first, even the strong form is true.
The second example violates the strong form, but satisfies the weak form.
But I don't understand. Non-extendable is what?
Non-extendable equal number of sides.
So 2 is non-extendable. This one.
And also 1 is non-extendable. Here,
But then
No, Sasha, the only requirement weak form is that the image, that C of T.
C of T is cyclable. So we don't require all of them non-extendable things are cyclic. But okay, it's okay. More and more strange.
So the strong form, all non-extendable types are cyclic. This is a strong form.
Yeah.
Weak form. We do not require that all non-extendable are cyclic, but we require that C of T is cyclic.
Yeah, and if a type is extendable, then nothing is required at all.
No, nothing. Nothing.
Okay.
So this is the most strange requirement.
Okay, so what is the next one? Less strange?
Less strange is the last one.
Oh, the last one.
This is the last one.
Yeah.
Net sites on the boundary. Actually, we do not need this requirement for substitution tiling, so we can just skip it. But it's very easy to understand it. So consider some vertex on the boundary of macro tile. Why can I?
Any vertex. Vertex, you mean just a vertex of a type? Yeah?
Right. So consider some macro tile and some vertex on the boundary. And consider the sites incident to it, these ones, 4 ones in this example. And only one of them can belong to the net. And if it happens, then this site, which belongs to the net, must be on the boundary, like this one.
So what is impossible? What would be the bad thing? Just draw something.
Let me choose color. How do I choose the color? I want to choose blue color, actually. So I can't choose blue color. Why? So, okay, what is bad? Bad thing is, for example, when the net goes like that. And good thing is when the net goes like that. When the good thing is when the net traverses the boundary of macro tiles, and bad thing is when it traverses some edge which has only one its side on the boundary. So this is bad.
Yeah, but why you say at most one side? How it's possible that 2 sides are used on? We cannot have two.
No. It's possible like that, Sasha. Like that. The net goes like that. So this is forbidden. This is bad because in this case we have 2.
Okay,
okay. Sorry, I missed how the site can be not on the boundary of the microtile if it's a vertex of the boundary of the microtile.
No, what like this? This side is this is a vertex and this is a side. So why?
So you mean if I have like just a grid and then I have a square and then I take a point, and so one edge can go. Yeah. Okay.
No, we take a vertex on the side, and then
Sasha, that's
the edge...
bad when it goes like that. That's bad.
Yeah, it's not allowed. Okay.
That's not allowed, and this is allowed. go straight out without traversing any edges which are near the boundary.
So do I right understand that in particular it avoids the case of a 2x2 substitution with square?
Of course, 2x2 is bad. So 2x2 doesn't satisfy the requirements.
Okay.
What I didn't understand here, what is bad?
Here, because
Yeah.
this side is
Which one?
traversed, this one is traversed by the net, but it doesn't lie on the boundary. The last requirement, and this side lies on the boundary.
But if it went something like this would be okay.
Right.
Just the problem is just because it's close to the boundary.
Right.
Okay.
And so that's it. No conditions more. So I at this point I can finish the talk and just say there. Oh.
No, I erased everything already.
Okay. Two main results. So if the substitution admits a markup satisfying the first 6 requirements, then the corresponding family of hierarchical tilings is Sophic. And if it also satisfies the last requirement, then even the family of substitution tilings is Sophic.
Why you say even? It's somehow obvious that it's more difficult.
No. Sorry. Just all of them, then the corresponding family is Sophic. Okay. Yeah. Now I will switch, and you should
erase
your correction.
Yeah. No, just if you will publish an archive, it's useful to know that Sophic is written in a different way.
Okay. And now comes a philosophical thesis. You can see that our requirements are very restrictive. Actually, among my examples, here is one example satisfying all requirements. This is the second example satisfying all requirements. And there is also the initial examples, this one, satisfying all requirements. So, so far we have only 3 examples satisfying all requirements. But the philosophical thesis is that actually almost for any substitution, using 2 tricks, we may prove that the family of distribution, both families are Sophics. And these are two tricks are the following one. The first one was very well known. It's taking a power of the substitution. And the second trick is sort of new. It's the trick of joining some tiles together. Let me just now provide several examples that will show that we can, using these 2 tricks, to prove sophisticity of both families for many distributions. So here are the first one. So the first problem is the lack of space. For example, if our macro tiles look like that, only 4, by obvious reason, it's impossible to make the markup. Because actually, I just forgot to say one thing. The central tile can't have vertices on the boundary. It's also required, I guess, or it follows from some requirement. So at least one tile should be an inner tile in a macro tile. So, and here is how we can avoid this requirement. So consider this substitution. This substitution doesn't have a markup, but then take a square of this distribution, this one. And for the square distribution, the markup is written here. It's you can verify that all the requirements are met for this one, for the new one.
Mm-hmm.
And now we claim that actually the set of hierarchical tilings and also the set of the family of substitution tilings are the same for the substitution in its power. For hierarchical tiling, it's sort of obvious, just falls from the definition. Is it clear?
It seems yes.
For substitution tilings, it's almost obvious. And it's not entirely obvious, because substitution tilings, we require that all patterns, finite patterns, can be seen in macro tiles. But for the power of the substitution, the family of macro tiles is a little bit smaller. And so there might be difference, but actually it doesn't happen.
What do you mean by smaller? No,
the set of super tiles for sigma to the k is smaller. So for sigma to the k, the super tiles are super tiles for sigma who of order which is divisible by k, right?
Yeah, but they are just a bigger one contains the smaller one.
Right, but the bigger one contains smaller one, so there is no problem here.
Yeah, okay. Yeah.
So is it clear, the first example, how we can just increase the space in macro tiles, just taking sufficiently large power? For example, it proves that for this substitution, we can apply both theorems. So the second trick, is that we can join two tiles together, or consider this trick using this example. So consider this substitution.
Yeah.
It consists of triangles, and so 2/3 requirement can't be fulfilled. But we can observe that for these, in these macro tiles, every triangle which is, so to say, angle up is adjacent to the right to a triangle that is angle down. You see? You understand what I'm saying? Angle. So to say, facing down is adjacent to facing.
But we have unequal number of this and that. We have more. We cannot group them into pairs because we are too many of. No, I understand what you want to do later, but just say something later, maybe.
Okay. Instead of this, consider this substitution, the second one. In the second substitution, we have also 4 parallelograms. One of them is written here on the left, and they are substituted as follows. We cut each such parallelogram. We obtain either two black or two white, or white and black, or black and white. Substitute both of them separately. We obtain a parallelogram which can be again grouped into parallelogram consisting of triangles which can be again grouped into parallelograms. So for new 4 prototiles, we obtain a substitution which is sort of equivalent to the previous one. What do I mean by equivalent? The set of tiles or tilings of the set of hierarchical tilings of the plane for the original and for the new are the same, and also the set of substitution tilings for original and for the new are the same.
So the new one don't have any triangle tiles.
No,
it has only...
no. For the new one, it doesn't have any triangle tiles.
And how it's cut? So how it's cut? You mean that you cut something like this? In the right-hand side, you should have also parallelograms.
Right. We group them like that.
Ah, so the tiles are here also parallelograms, not triangles.
Yes. In these simple examples, we do not need triangles. We will consider more complicated examples when we also will need triangles. But up to now,
so in general, we combine original tiles with new tiles, or what?
Right. In general, I will explain this later. This more general situation. But for this, we can just prove the following lemma. If forget about lemma. Let's just consider this example. So this new substitution admits a markup satisfying all the requirements, which is obvious, right?
Because not that obvious. For example, we have what will be the center? We need to choose for this. We need to
choose any of the 4, whatever which you like.
Just you can choose any of the 4.
Right, this one, and just write that and that.
But if I change it, if I take whatever I want, then who knows what will happen as a cycle? You have some requirement about the cycles, the central tiles, and the labels, and blah blah blah. Why it's so obvious that we will have it?
We will discuss that later.
Okay.
This allows just to meet 2/3 requirement. I do not claim that we also meet the remaining requirement. So more or less assume that all the other requirements somehow will be fulfilled. And this is the trick explaining how to meet the 2/3 requirement.
No, but it's just in this case you have triangles and you have now parallelograms, so it's easier to meet 2/3 requirement.
Right.
But why something happens like this in general case, it's not clear.
Not clear, yeah. But I want still to finish this example.
Yeah. Okay.
We need to prove. So assume that somehow we have labeled this new substitution satisfying all the requirements. Assume that.
Yeah.
Why it implies that the original substitution is also good, meaning that both families are Sophic. Is it clear?
But in this example, it's more or less the same families, just cut in different things, no?
No, Sasha, it's not that way. So assume that you have designed a decoration and local rules for parallelogram, right? So how do you design the decoration?
You mean the parallelogram thing? So yeah. Sorry.
And this is done as follows. So this sloping diagonal, which cuts each parallelogram into one, should be assigned a very special color, which is not used everywhere, anywhere else.
And in this way, we force them to group in
Right.
parallelograms. Yeah.
Right. And then it's very special color will force to group them into parallelograms, right? Now,
Good.
these two tricks sometimes can be used together, and this is the most interesting example called it's called how Robinson stone inflation. So this is about Penrose tilings, but let's start with this particular substitution. So the problem with this substitution is that both we have triangles and also lack of space. Now, what we will do? We will take a large power, and then we will group tiles after that. And we will, after that, we will meet all the requirements. This is done as follows. Take the 6th power. Maybe 5th is enough, but for the 6th, it's very easy to do that. This is the 6th, the macro tiles for 6th power. Let's make it larger, like that.
How did you make the picture? It's just you wrote all the colors yourself, or you can have a program which produces it?
Colors are made by hand.
Oh, for all the small tiles.
It's
Right.
not very long to do that by hand. You
No,
can,
not very long, right?
Okay.
So these are macro tiles.
substitutive. So,
Yeah.
And this is the sorry. And this is the joining. So how do we join? We join tiles in rhombuses, like here. And now some of them will be will do not meet their pair, and so they will remain as they were before. So
Can you show what is the grouping on this, just on this picture? So where is the central tile first?
the central tiles, though, you see here is the central tile,
Just this rhombus.
right? This
Yeah.
one.
And where are the other rhombuses and where are the triangles?
Purple and so triangles are white only on the boundary. Triangles are white and they are on the boundary. Rhombuses are of two types: blue and green, blue and purple. Blue are called large rhombuses. Purple are called small rhombuses. And in this particular example, the initial tile is triangular, but the central tile is rectangular. So the initial triangle tiles is extendable. And so the green graph, the connecting graph, includes also the central tile. You can see it on the picture.
Yeah. It
So
uses the remaining edge of the central tile because it exists. Yeah.
it is a necessary condition. I forgot all the conditions. It's a necessary condition that you can meet the connecting net to the central tile, or it's just
it's a requirement. It's the requirement. So necessary condition, right? We need this.
Okay.
And this is
okay. So
Sasha,
the
erase your red color.
Yeah. Sorry.
So this is the image of the second triangle. And the central tile is now here. It's a small rhombus. And again, we group almost all triangles into rhombuses, except for some triangles on the boundary, because they can't group with anything.
Yeah, but now we should also split the
You mean this?
this is one, yeah, rhombuses.
The rhombuses. The rhombuses are split into triangles. We apply the substitution to both triangles, actually to 4 triangles. And then again group. And then mark up the resulting macro tile. So here the rhombuses are non-extendable, because the central tile is also a rhombus. And here is the last picture. Here is the image of another rhombus. And all the requirements are met. So the number of prototiles is increased. So we take the initial triangles and also now the rhombuses. We define the new substitution on this increased set of prototiles, and we make the markup. And again, by main theorem, the resulting families of substitution and hierarchical tilings are Sophic, and as a result, obtained for the initial family substitution, they are Sophic. This is how these tricks work together.
But with a strange thing, so you have this white triangles only on the boundary.
Right.
So if you even don't have kind of substitution for the for these white triangles and use only substitution for rhombuses, you will get something very similar to tilings, just with some small part on the boundary, yeah, or not? So imagine we apply again the substitution to this thing. Just we don't know how to substitute the triangles, so we skip them. But still, we have a big part covered with rhombuses, yeah.
Right, but you are right.
And so we don't need the triangles really to get something infinite.
We do not need triangles, but we want formally to reduce, to apply our theorem without thinking in the direction you proposed. And this is the way just to apply the main theorem. For initial distribution, from initial substitution, we build the new one, and the new one meets all the requirements. And then we prove that the families, since that if the family of hierarchical tiling for the new distribution is Sophic, then so is the family for original one. That's how I propose to to reason. But that's not it. This solves only problems with 2/3 requirement and just lack of space. And recall that we have other requirements which are not always easy to meet. The most so we had these names. This name of size requirement, but this is usually very easy to meet, and that's because of the following problem. If we just carefully use this path without bending them that much, then the angle between the initial side and the angle between the corresponding side of the central task will be small. And when the angle is small, the first requirement will be met. So you see, when two prototiles are shifted so that they share a side, then the normals to these sides form an angle, the angle of 180 degrees. And so to violate this requirement, we actually need to take special efforts. So it's very actually hard to violate this requirement.
Okay.
So that's why we usually do not care about its requirements. It's sort of automatic. But the main problem is with this cyclicity requirement. How to meet it in the weak form? So the weak form will be enough for us. When I stated our theorem, I meant the weak form. For the strong form, the proof is much more easy than for the weak form. But the strong form is sometimes hard to achieve. For example, for this second example in the bottom, whatever power you take of your distribution, you can't achieve the strong form because the
But if we take a second power, we just have only green tiles, yeah? Everything is replaced to green tiles. What are the problems then?
Sorry, I'm lost. What are weak form and strong form? It seems that they are the same.
No, you in the second one you require cyclicity not for all tiles, but only for tiles which are image of something.
which are
C of T is cyclic.
But,
Here C is cyclic, and here T is cyclic. This is difference. That's what Sasha Kazachinsky explained.
I see. I'm lost in the text. Okay, yeah.
So Sasha, recall the graph here. So this is one. When you take a power, you will still have two different green guys, right? Sasha, you are not right. When you take the square, still it will have one blue tile. Because when you replace green...
green will, it will have many blue tiles, actually.
Right.
Yeah. Sorry.
Not many. No. Not many, only one, I guess.
No, each green thing will have a small blue thing inside.
Right.
So you get something like you have this here and here and here and.
All right.
Yeah. Okay. So yeah. That's wrong.
Okay. So what I want to say, how to meet this requirement. So assume that you have met all the requirements except this one. I will explain then how to meet this one, not violating all the remaining one. And this is done, again, you taking a power or a distribution for the big one. So here is an example when even the big requirement is not met above the line. So you see what is the graph here. So we have, let's write here 1, 2, 3, and 4.
So this becomes green.
So
and this becomes red.
4 maps to 4.
And this becomes red.
3 maps to 4. 2 is mapped to 3, and 1 is mapped to like that.
Yeah.
So 4 is cyclic, right?
But in the image we have also 2 and 3.
In the image?
No, it's for 2 and 3, the requirement is not fulfilled. They are not cyclic.
So 2 and 3 are not cyclic.
Yeah. So this is a problem with this thing. Yeah.
But then take the second power. For the second power.
So green becomes red, and red becomes red. Yeah.
So
red becomes red, and
so red 4.
Yeah.
Right. Everything is mapped to red, right? 1, 2, and 3. Here is the graph of the function for the square of this.
So, but green is mapped.
Green is mapped to different red, which is not cyclic, right?
Yeah. But in your picture, where it is, I try to draw it on over the tiles. So is it? So we have several reds in our graph.
Right. So sorry, this was a mistake. We need to simplify the initial. For this, we need to take a power which is larger than 2. Sorry, that's a mistake.
But why you think that if you take a larger power, we just what we take? We just take a iteration of the mapping.
Right. So we do not need.
And then iteration is just one maps to 3, 2 to 4, and 3 to 4.
Just forget about this. So and so forget about this also. So we do not need these. Then the initial graph will be like that: 2, 3, and 4. And after taking the second power, 2 will be mapped to 4, and 3 also will map to 4, and 4 will remain cyclic.
Yeah.
And actually, one can prove that this trick works always. So taking a not sufficiently large, a spatial power over original distribution, we can also meet the cyclicity requirement. And also, if all the requirements before were met, then you see that the power increases the space. About the names, it makes different names different. And so all the requirements, names requirements, 2/3 requirements and other requirements will be met also for this, but of course for a new markup, because after taking the power, we need to design a new markup. So this is not a theorem. It's just a claim that if you give me a substitution, most probably with these tricks, I will prove that the resulting families are Sophic, both of them. So here is no theorem, just some claim.
And what about, for example, the pinwheel tiling? Do you think it is Sophic with this?
But
pinwheel is not of the type, correct,
right,
because it has infinitely many things,
right,
because we are not allowing rotations.
Right. So it doesn't apply to pinwheel.
Just because of the rotation?
Right.
No, maybe one can change the setting and allow rotation, but this is something different.
Right. Yeah. Maybe you can adjust the theorem also to pinwheel case, but up to now it's not. It doesn't apply to pinwheel.
To me, the problem with pinwheel is not really the rotation, but the fact that there are tiles which are adjacent only to one other tile. But maybe with all your requirements, it can be work it out. I don't know.
Okay, so that's it. I didn't dare to explain more in this session. And now I can say some blah 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 explaining why we need all these requirements.
But let's still try to understand the status. So you say that these requirements are needed for the statement in Vereshchagin paper, yeah? And you don't know how to prove it without these requirements, or you know that it's false without these requirements, or what?
I can prove that I can provide some examples of substitutions in which their technique doesn't work. So some of their claims are wrong. But I do not have the proof that the resulting families are not Sophic. Just the claim are wrong.
Some intermediate statements which are used to prove that they are Sophic do not work anymore.
Right.
Mm-hmm.
So both 2/3 requirement and the cyclicity requirement are crucial for the technique to work.
Mm-hmm. Okay, say something philosophical then.
Okay, I can explain now how we can prove this. Oh, sorry. Oh, let's consider, for example, this picture. First of all, as local rules, we will use the rules which are the simplest rules, the rules of Van Hao. So we will just cover the sites, and the local rule will be that when two tiles share a site, then the colors match. So the technique is from Vereshchagin papers, almost all the technique. So the coloring will consist of 3 indices. So the first one requires the tiles to assemble into macro tiles. Let me still try to use the color. Misha, how to choose?
Just there is some point in the menu, which is a color point. You can try it, and it will change the color.
Коля, you should tap on the left and look at circle with.
Там внизу есть такой кружочек в этой линии, где все картиночки.
Да, ну.
Так ты можешь нажать на этот красный или синий кружочек, и появится меню с другими цветами. Нажми на него карандашом.
Сейчас.
Sorry for Russian, but I guess it's not. Но там кружок, есть цветная такая штучка, ее легко найти, потому что она цветная.
Она у меня черная.
Она того цвета, которого ты хочешь
рисовать. Я понял, почему я не вижу, потому что она у меня черная и фон черный.
Окей, yeah.
Now I have so, for example, first of all, we just number all the types like 1, 2, 3, and so on. Then
in all things, so you will continue
in
the
all
number.
macro tiles. So so just number all the types, and then, for example, the column will be like that. The central index, which will be erased later, will be just the type. For example, 2. Then on the side shared by 1 and 2, there will be the index, red index 1, 2. The pair of 1 and 2. In the first element is the left side. The second is the one side. Right side, right tile, the type of right tile. So the coloring will be like that. On this we will have 1, 2, and on that we will have 2, 1, also 1, 2. And so all the for each type we will obtain one tile which has red indices on their sides. Now, on the outer sides, when there is no neighbor, we just write the number of that side from left to right, like 1, 2, 3. So, for example, here we will have 1.
And here, what we will have here?
Here, 1, 1, 2, 3.
So we continue the numbering from
1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3, from left to right.
Okay.
So, for example, we will have now many rhombuses like that. One of them is of type, say, 20 with 1, 2, and one of them is of type 1, 2. So this is the local information present. This is called the local information present on the sides of tiles. But that's not it. There will be also the global information. The global information will consist of 2 indexes.
So let me ask. So for now, if you look at the tiling, side-to-side tiling, they by construction they are grouped into macro tiles, because the local this edges, internal edges, can match only as in macro tiles. So you can group them automatically into macro tiles. This is not a problem. But then the problem is why these macro tiles satisfy the same rules so you need to show that the rules are true for the macro tiles. This
Sasha,
is the problem, yeah?
And also they will be just adjacent only macro side to macro side.
This is another, yeah. That's another thing which you need to check.
So these red indices require to assemble tiles into macro tiles that are macrosite to macrosite. But it's not enough. This will require, this will prove that any proper tiling, proper means that it's side to side and the colors on the edges and side match. That each proper tiling is partitioned into macro tiles.
Yeah.
But we need to ensure not only one step of this grouping, but infinitely many steps. What does it mean?
So
Infinitely many steps. That means that in any super tile, so consider some super tile of order, say, 20. And this super tile should somewhere keep the information about what will be the type of this super tile after 20 compositions. And this will be present in several places as green and blue indices. So somewhere in these tiles, in this macro tile will be information what happens after 20, if this is the super tile of order 20, after 20 compositions. And this role will be will be done using green and blue indices. More precisely, it's enough to have only green. So green indices will have this information. Let's write it green. And also, because of this super tile of order 20 consists of some super tiles of order 19, in any of these 19 guys, there is also information of their type, which will be obtained, which type has this super tile of order 19, and so on. So each tile will have this local information, red information, and also this blue, green information, which is global one. More specifically, when we consider these macro tiles, then this green ring, all the sides on this ring, like this one, and so on, will have the same green information, which is equal to the type of them type of the tile obtained when this tile is composed. So that's the first idea. And this central tile, together with all these blue things, will carry this information, this green information. So this, for future use, when we will compose this tile together, this green information will come here as green information. So assume that we have something here, it will come here. When become some green here, it comes here, and so on. And this will be used later.
So, but maybe it becomes too philosophical for me. But can you maybe say just one sentence? What is difference between green? What kind of information is transmitted along green lines? And so this information is transmitted because things which connected by a green line should be coincide in some respect, and things connected by a blue line should coincide in some different respect. So some information is transmitted along the lines of both colors. Yeah.
Right. So what is the difference between the green and blue?
Which kind of information? Yeah.
Sasha, the same information. So the difference is that this information refers to different steps, levels. So the green connecting graph carries information about the first step, and the blue carries the information about further steps, and we don't even which ones. It might happen that this particular tile carries the information about what happens after 20 grouping, 20 compositions. And so each ray will carry a piece of that information. That's the idea. So on this level, it's hard. It's just blah, blah, blah. It's very hard to explain what happens.
Yeah, but maybe Andrei understands this and can explain something because in comparison with what happens with this fixed point tiling, no?
No,
it seems to have some similarity, but this I can say. Okay.
So maybe I will start with the proof in the next talk, and we will see how it works, everything.
Okay, no, today is a bit better than I expected. So I thought that I will be confused more, but don't know how. But also the last question. So what is the position of Vereshchagin and Langer about this paper? Indeed, the proof is incomplete and requires additional condition, or some reasoning can save it.
For me, in this paper, we wrote some part at some point the definition of what is a good substitution.
Yeah.
And basically, the definition is a substitution is good if the construction works, which is not very satisfying because you don't really know what is a good substitution. In particular, you don't.
So you mean that conditions are not formulated explicitly, or what?
Yeah, far from being explicitly. We have checked it for the 3x3 square. I wrote in the paper an example with the rosy tiling, the rosy substitution. Which
but Kohler says that conditions are clear, but the proof is not complete. But
for me, the conditions are not clear.
Okay.
They are not explicit. Actually, it's one of the open questions is written is characterize what is a good substitution. Mm-hmm. And it's more or less what Nikolai is trying to do is to you really need to know what means good. It's not just
so you prefer that I write that the conditions are not clear also in your paper, right? Okay.
Yeah. I say more precise that not clear. They are not explicit here.
Not explicit. Okay. Yeah.
I mean,
like in Goodman-Strauss.
No, in Goodman-Strauss he claims that they are clear, but it's his claim. No, other people cannot confirm this. But
yes, it depends on the viewpoint. I cannot say about Goodman-Strauss because I never managed to read the whole paper, to be frank.
Yeah.
So maybe they are explicit, but maybe they are too explicit. So.
Okay.
But I think that there is we could do two things. One thing is explain how this the index works and so on. For that, I don't know what you think, Nicola, but I will explain it only on the 3x3 square because it's much simpler and suffices to explain the idea. And the second thing, which could be more interesting maybe, is that you take some list of well-known substitution and you show, for this substitution, for example, half-X substitution, swing substitution, the chair substitution, the table substitution, or something like that. You say, okay, this works. My conditions are satisfied if you go to you inflate 6 times or 7 times, and with the drawing of the nets and so on. It could be nice, no?
Yeah, and I want also to add that in your paper, even for 3 by 3 square, I mean, you verified it, you say, but the verification is not in your paper. In your paper, still you do not have a complete proof.
For this,
Okay,
For this 3 by 3.
For that, I agree that there is a fault in the paper, which maybe it's still in archive, that we correct when we were in serious. But for me, it worked perfectly for 3 by 3. Actually, it was also for 2 by 2, which it can be another discussion. But so we don't need those every time so strong condition. But
so your technique, in my view, works only with this requirement, which is called strong cyclicity requirement, and you do not mention it at all in your paper. This one.
Mm-hmm.
Yeah. No, but let me make a more general critical comment. So it would be nice. So there are something mystical happens when we have so many nice Sophic tilings of geometric type and many proofs of them. So no, I can imagine that if you have a very simple condition, and even if you have a very difficult, if it's very difficult to check, then you can at least remember the condition and then see that, okay, we don't have a clear proof, but still we have a clear theorem which we can use. But up to now, both the conditions and the proofs are quite complicated. So I also can imagine there is a simple proof, and then there are some conditions saying that this something should happen to make the proof work. More or less, as Thomas says, we require what is needed in the argument. But if both things are complicated, it's kind of disturbing.
I would say that the proof, if you take only the 3 by 3 square, the proof is not that complicated. It's not that simple, but it's typically
okay. No, but 3 by 3 square, we don't need anything. We can just explain it from general. So this is if we need a theorem for rectangular substitution, for square substitution, then this model theorem is indeed true, but we don't need geometric argument for that. We can just
yes, but first the paper of Moses. I don't know if I did not manage to read all. At some point I was stuck.
No, but you can do it easily using fixed point. Actually,
it's what you do. You just explicitly construct a fixed point.
No, but then why we need this explicit construction if there is a kind of general one? No, but anyway, the idea, the kind of a miracle which need to be explained is why so many nice geometric substitution give Sophic tile sets, and kind of it would be nice to have some kind of general understanding how to prove things like this, but how to get a simple proof. But this is a pity that proof is still complicated. I don't know whether it's possible to get a simple one, but
to be frank, when you look the proof for the 3 by 3, I think it gives a fairly good idea of how it can be extended to geometry, especially if you add the additional condition of Nikolai, who make it clearer how it can really be extended. But the proof itself is really combinatorial. It's more easy to explain it with 3 by 3 squares, but but
the
entire, it's not really connected to that.
But the entire idea is to have tools to deal easily with geometry, because with squares, more or less, there is no geometric problems somehow. And okay, no, it's just a dream if it's not.
Oh, but I mean, it's what Nikolai is doing. is to precise the geometric condition.
Yeah.
Not in a like a what to say.
No, I'm just saying that this is still things to dream about, which are not something easy would be very, very desirable. But okay, if we don't have, what can we do?
So we know that there are no uniform bound on the length of the shortest proof, so maybe there is no nice proof.
No, but actually, there's too much miracle happening to say that it's just a coincidence. It's very, very, very nice pictures, and the pictures are much more nice than the proofs here, and this is what is disturbing. Okay, so next time we will have a continuation of this.
Right.
So finally, I managed to download the file and map it, put it on YouTube, and I hope Misha Raskin will send this one again, so we can have it. But
okay.
Kolya, may I ask what you want to explain next time, because I cannot be here next time.
The proof, I guess.
The proof.
Okay.
But don't worry, it won't be. I guess it won't work.
But I prefer
so you
to skip the
don't
proof. Maybe there will be a fourth seance about examples. I'm more interested in what you have done for the geometrical condition, and to say how it works for a real example.
I think I won't explain the entire proof. So some two lemmas will be stated without proof, I guess, but the rest will be proven.
Yeah. Also, there is another request for Kolya or for Thomas or for anyone else. So if someone can explain this Einstein story in a understandable way, this would be great.
Oh, right. I agree.
And sometimes you even thought that maybe during your course you will prepare this proof for exposition.
Which story? What?
No, this is Einstein. This Goodman Strauss and other people found one specific tile, which geometric tile with which is a form of periodic tiling. Ну, это знаменитая вещь несколько лет назад была, что вот они придумали такую одну хреновину, которая замощает плоскость только не периодически, один многоугольник, не выпуклый.
Ну да.
It's called Einstein because it's Ein is one and Stein is stone.
Саш, только он выпуклый.
Нет.
Нет, выпуклый не существует такой. There is a theorem which says that there is no convex Einstein.
Not convex.
Not convex.
Yeah.
But actually, there is not that much to explain in the proof. They just give you a tile and you check that. So it's by computer mainly to check that you can only make meta tiles. And
no, okay. If it's just a kind of some simple structure plus computer search, this is okay. But it would be interesting to see exactly the structure.
They have as I understand, they have two different proofs, and the second one explains why the construction works not for one specific tile, but some parametric family of the tiles. And this second argument, it's not just verification of some case study with a computer. So there is some argument behind it.
There is another paper actually, which is maybe better to read. Is a paper by, I think it's Akiyama. He writes about the Einstein tile. So there is this whole family, and he shows that okay, for some parameters, the substitution is more nice. It's really a substitution, like as far as I understand, it's really a substitution where you inflate the tile and cut it again. Because for the one which is written in the original paper by Goodman, Strauss and other, it's not, the substitution is a bit strange. The way you get the meta tile from the tile and so on. I tried to make a talk about this, and I thought I can really do by myself the pictures, but actually it's not that simple.
Okay, so let's then continue
Okay,
next
bye
time.
bye.
No, actually, I can also make a request. I can give a talk of Mathieu Rosenfeld, or we can maybe even invite Mathieu Rosenfeld. He proved something nice about. There is a combinatorial thing that's about approximations of numbers. So let's say that fix some epsilon and say the denominator is good for number alpha if a multiple of this alpha always have some multiples of this alpha. For example, 2 alpha, 4 alpha, 8 alpha, and so on, never are epsilon close to integers. And so there is a theorem saying that there exists for every sequence of denominators, there exists a good irrational. And this can be proven. It was quite a longer problem. And now there is a very simple proof using some word avoiding pattern avoiding story. But so he explained it to me, and now I understand it and can even explain it. It's a nice short thing. Yeah, okay.
Bye bye.
Ouais.